They come from weighted averages. Think of the way your grades are weighted. Major grades have a higher percentage than minor grades, and they have a really great impact on your overall average. Similarly, atomic mass is a weighted average of all naturally occurring isotopes of that element. Remember, isotopes, same number of protons, but different number of neutrons. And because they have differing number of neutrons, they have different masses. The atomic mass takes into account both mass of the isotope and relative abundance. So let's get your calculators ready. In your notebooks, you've written down two things: that atomic mass is a weighted average of all naturally occurring isotopes, and it takes into account not only the mass of that isotope, but how abundant it is in nature. So there are some isotopes that are very, very abundant, and there are some isotopes that are not abundant at all. So according to your current experience with your weighted average, the more abundant a number is, the higher or the more likely it will affect your overall grade. So major grades, because they are more abundant in your overall average for the 6 weeks, your overall weighted average will be closer to your major grade average than your minor grade average. So what were those things that we had to take into account when we were calculating average mass? The first thing we wanted to look at was the mass of the individual isotope, and the second thing we wanted to look at was its percent abundance. So this first step that we have to do is figure out how many total isotopes are there for an element. And I'll give you a very common one. Carbon has 3 naturally occurring isotopes: carbon-12, carbon-13, and carbon-14. That's step 1. How many isotopes naturally occur in nature? Step 2. We're going to multiply the mass of each isotope times its percent abundance. Percent abundance just means how popular is it in a sample if I were to get it naturally in nature. So if I go scoop up some carbon, how many of those would be carbon-12 atoms, how many would be carbon-13, and how many would be carbon-14? And the last part, number 3, we're going to take the sum of all of the new masses. So at the bottom, this is the overall formula that we'll use to calculate average atomic mass. Atomic mass is equal to mass of the isotope times its percent abundance, plus mass of the other isotope times its percent abundance, and this formula continues until I have multiplied every single isotope times its percent abundance. All right, here's how we do this. Our first example, element X has 2 natural isotopes. The isotope with mass 68.956 atomic mass units has a relative abundance of 60%. The isotope with mass 70.954 atomic mass units has a relative abundance of 40%. Calculate the atomic mass of this element and name it. So the first thing that we have to do, actually, the first thing I want to do is take a look at these numbers, these percentages, and I want you to think about what that means. If I were to have a sample of 100 of these atoms, we don't know what their name is just yet, but I have 100 of these atoms. It looks like there's only 2 versions of this atom. There is the atom with a mass of 68.956 and the atom with a mass of 70.954. It looks like out of 100 atoms, 60 of them would have a mass of 68.956 and 40 of them would have a mass of 70.954. So I want to take those percent abundances into account when I get my average. So because more than half of the atoms have this mass over here, 68.956, my average should be closer to 68.956 than it is to 70.954. So I want to find the mass of each isotope and multiply it by its relative abundance. So what I like doing is taking my mass numbers, 68.956, and I'm going to multiply it by its percent abundance, which is 60%. Now for all my math whizzes out there, another way to write 60%, and this is just to make the calculator part of our calculation easier, 60% is the same as 0.60. And that's the way we calculate that would be 60% is 60 out of 100. So if you're having trouble making that conversion, you simply take the percentage and you move your decimal over 2 places to the left, and that becomes your decimal version of that percentage. Because I didn't want to press all those extra buttons in my calculator, I simply take my percent abundance and I write it as a decimal. So 68.956 times 0.60. That's my first isotope. And in fact, what I want to do is I want to show you what these numbers look like. I am going to pull out my calculator. And I want you to type in 68.956 times 0.6. And I'm just going to write it down here. You don't have to do the same thing, but I want to show you what I'm doing here. 41.374. Okay, so if I take this 68.956 and I multiply it by 0.6, I get a little bit more than half of this original number, 41.374. So now to finish up with this average atomic mass, I'm going to add second isotope. Its mass is 70.954, and I'm going to multiply it by its percent abundance, which was 40%. Now remember, I don't want to do the percentages in my calculator, so I just move that decimal 2 places to the left, and it's the same as 0.4. So now in your calculator, I want you to type 70.954 times 0.4. And my answer is 28.382. So what I wanted you to see here is because I multiplied by a smaller decimal, my answer here at the end is much less than this one over here. Now ultimately what I'm going to do with these two numbers is I'm going to add them together. You can do them separately or you can do it together in the calculator. In fact, I recommend that you would just put it in your calculator all together. But when you add 41.374 to that number, your average mass is, I'm out of space here, so I'm going to get rid of this for now. My average mass is 69.756 atomic mass units. I'm not going to forget to write my unit because that is points off on a test or a quiz. I'm going to look at this final answer and I'm going to come to some conclusions. Is my average closer to 68.956 than it is to 70.954? When I'm looking at my average 69.756, it does look like it is indeed closer to 68.956. And I want you to think about it this way. 68.9 is super duper close to 69, and 70.9 is really close to 71. So if I look at my average here, it is indeed closer to the number 69 than it is to the number 71. Now the last thing that we want to do is identify who this element is. So I want you to take a look at the periodic table and see if you can find an element whose average atomic mass is close to 69.75. Now I don't see exactly 69.75, but I do see 69.723. So I'm going to call this element gallium, Ga. Let's make an inference. Which isotope of nickel is most abundant if the atomic mass of nickel is 58.69 atomic mass units? So look at your weighted average, 58.69. Look at all of the isotopes of nickel. Nickel has 1, 2, 3, 4, 5. Nickel has 5 different isotopes. Now, if the weighted average is 58.69, which of these do you think has the highest percent abundance? And I'm hoping you said that it was nickel 58 with a mass of 57.93. It has to be the isotope with the highest abundance because the average mass is closest to that number, 58.69. All right, so far we have described atoms. They have protons, electrons, neutrons. We know where they're found. We also can compare them to isotopes. So isotopes are atoms with the same number of protons, but differing number of neutrons. So this says to list the 3 subatomic particles. It's actually already done for us here in this table. And then fill in the table below. So for protons, their charge is a +1. Ooh, I can't see that at all. +1. and their mass is 1 atomic mass unit. For electrons, their charge is -1. Their mass is 0 atomic mass units. For the neutron, it has a neutral charge or no charge, and its mass is also 1 atomic mass unit. Give a one-sentence summary of the difference between an isotope and an atom, and I will let you do that all on your own. Now compare. So now that we have reviewed the similarities and differences between atoms, ions, and isotopes, I want you to be able to fill in the Venn diagram with what you've learned so far.